Recording this. Okay, so now some administrative issues. There are a couple of people who have written to me that they do not have an account on Moodle. Now I've noticed that when I was putting in everyone's name in the Moodle rejected 4 or 5 email IDs, and I was told by the administration people that some of these people may not have registered yet, so that's why their names are being rejected. So those of you who are having problems logging into Moodle, first check whether you have registered on time, whether you're registered late, and after registering, your names have appeared in an official file or not. So I think that you should go and check. So that was the administrative part. The second thing is that you have gotten your assignments. You would have done one assignment. There was one person who shared the problem that the Mac he cannot install Kyle tool on Mac, which is correct. And so he has asked for access to our department's computer. So I will have to check with our system administrator Nimish Bhai and see what he says. We are going to have, as I told you last time, we would like to have 2 parts to the midterm. The one would be the actual midterm, which will be held on 28th. And probably I would like to take one on Thursday, which is almost 90% sure. I mean, you have to study for both, so and there will be same course material. So keep preparing. I just need to check out some issues which I need to make sure to take care of cheating problems, because I don't want people to cheat a lot in that thing which we are going to conduct on Moodle. Once again, regarding cheating, I've told you, do not help others to get as many marks as you do, because you are cutting your own foot. So that I mean, if you get an A and if you help someone also get an A, then what's the point? I mean, outsiders would think you are as good or as bad as the person who has cheated. That's number one. Number two, people look at your overall performance. When you graduate and you go out for a job, or entrance to a university in foreign countries or even in India, they would look at your thing in overall perspective. And if they see that in couple of semesters where performance was very good, and then it started going down, so it does not bode well, because then at least the Indian companies would be definitely sure that this you have gotten this inflated grade due to cheating. So you don't want to have that. I mean, your performance should be consistent, either continuously going up. You may have done something bad in the first semester, but then the scale should be going up. Or if you have done very well, then you should maintain that. But you've done bad in the first semester, and then very good in couple of semesters, and then performance again going down because then in-class exams are being conducted. So I mean, that is going to be a problem. So if you have any administrative question, you can ask right now. Otherwise, we'll move on to our academic topic. Okay, so let us move where we left off yesterday. Can you see the slide?
Yes, sir.
Okay, good.
Yes, sir.
Excuse me, sir. Yeah, just
Yes,
wanted to ask
go
a
ahead.
doubt. So the second midterm quiz which you said would be on 23rd, right? Next Thursday.
Yeah, possibly, yes.
Okay, thank you, sir.
Okay. You are going to have quiz. Whether it will be counted or not, it's a separate thing, counted towards your final grade. But most definitely, you will be having most probably you will be having a quiz, and you need to perform well in that. Okay, so we were talking about pipelining, and in pipelining we saw the advantages of having a pipeline. Then we also said that how many pipelining, how many pipeline stages should we have? Here you can see we have got 4 pipeline stages. And then, as we discussed earlier, that, if you divide up the work in smaller and smaller parts, then, your throughput can increase. So once again, I would like to tell you the difference between latency and throughput. The latency is time taken by an instruction from, beginning of the fetch stage to the end of the write stage. And that is known as the latency for execution of one instruction. Now, increasing number of pipeline stages will not reduce latency. Latency will more or less remain the same, or if you want to be very, very strict about it, then it may increase a bit, because you have to account for setup and hold time for the sequential circuits or the latches or flip-flops which are there to separate out 2 stages. But your throughput would keep on increasing, because now once the pipeline is filled, this word is very important, because initially first 5 instruction would take more time. First instruction, you will say that it will take 5 cycles, a 5-stage pipeline. The second instruction after that will come in 1 cycle, and then rest will also follow. But usually when we talk about throughput, we say that once the pipeline is filled, then you can start getting 1 instruction after every cycle. So this is what we want, and that is the throughput. That is number of instructions getting executed within a fixed time period, and usually it is 1 cycle, and 1 cycle is basically the time period. So if it is like 1 gigahertz processor, then the time period is 1 nanosecond. So 1 cycle is worth 1 nanosecond. Okay, then we said that there are certain issues. The first issue is, what we are going to talk about today, is data dependencies. And we talked about 2 instructions, I and J. Now, these 2 instructions, I and J, could be anywhere, right? J could be immediately followed by I, or there might be 2 other instructions or 3 other instructions between them, or there could be 100 instructions between them. We don't know at the moment. But one thing we can definitely say, that there is a data dependency between instruction I and instruction J. Why? Because instruction J is using the value of R1, which will be calculated by instruction I. So that means instruction I should always be calculated before instruction J, right? That is what RAW says. RAW means read after write. So first, you have to write the result into R1, and then only you should read the value of R1 for the following instruction. Now, having said that, then you may start wondering that if J is after 100 cycles, would it make any difference if there is data dependency, or J is immediately following after I? Will it make any problem? Because dependency is a program property. You can't do anything about it. So if your I is producing a result and instruction J, which is the next one, is going to use it, that is a program property. You can't do anything about it. But the problem which we will have is whether the dependency will be converted into hazard. Now, hazard is a dangerous thing. It will give you wrong result. Dependency is a program property, and it may or may not convert it to a hazard. So dependency is not always dangerous. Just have to keep that in mind. But hazard is always dangerous. So what we saw here, let us say that instruction J is immediately following instruction I, right? So there are no other instructions between them. And this is your time scale, that this is t equal to 0, t equal to 1, t equal to 2, t equal to 3, t equal to 4, t equal to 5, and so on. Now, at t equal to 0, you will fetch the first instruction, which is I. In second cycle, the first instruction will move to the decode stage, whereas the second instruction will be fetched, and then it will start moving. But the problem which arises here, and we saw that in the decode stage, the processor or the ALU would expect that you would give it the value of two source operands. So for J, the source operands are R1 and R3. So it would say, go to register file, read the value of register R1 and register R3 and give it to me. But we have a problem. Because of this dependence, you need the latest value of R1, which will be written by the instruction immediately ahead of it. That is instruction I. But according to the processor which we have designed, that will be written at t equal to 4. Correct? And this demands the value of R1 at t equal to 2. So now you see the problem. You can't go back in time. I mean, R1 is not yet written, and at that time you want to read the value of R1 from register file. If you allow it to read from the register file, it will definitely give you a wrong or old value of R1, which you don't want. So that means you will have a problem, and your program will go wrong. Now, you may be wondering that, before studying this, when I used to write a program, I never used to worry about such thing, data hazards or data dependency. I just wrote a program, and if the program was logically correct, it gave me the correct answer. So in this particular lecture, we are going to see why you are getting correct value, even if you write two instructions, one after the other. And in fact, it is the job of an implementer to design all these safeguards so that a programmer may write a program in any way, but at least it should be executed correctly and according to the programmer's logic. Okay, so we have seen the problem over here. Now, the first solution is that the second instruction, that is J, should be stopped at this decode stage and don't allow it to move forward. Right? So you wait for 2 cycles for the second instruction. Let first instruction go through. But you know the meaning of this. If you allow second instruction to be halted for 2 cycles, all other instructions after it, that means third, fourth, fifth, sixth, will be coming 2 cycles late. So this is one solution, that you wait for 2 cycles. Once the value is written into register, only then you read it and then supply it to ALU, and then you move forward. But there might be many such dependencies which can convert into hazard. So every time you start pushing in bubble or no operation, this is also called as a no operation instruction. So it's something which is used by compiler. It will send in something called no operation. So if it is no operation and second no operation here, that means you solved the problem, but you waited for 2 cycles, so you are making your execution slower. And no designer would like to give you an answer which is slow. You want the answer to be quick. So this is a possible solution, but not a good solution. Now people will think about the next thing, that you may write the value into register R1 in this stage, but the value of register R1 is already determined at the output of ALU, right? Because the value of R1 will do nothing in the memory stage, right? Because any logical or arithmetic instruction does nothing in the data memory stage. So only load and store are active in the fourth stage, where they access memory or store something into memory or load something from the memory. Other instruction just floats by. So they say that, can we do something? And that particular thing, what you can do is known as data forwarding. So this is on the time scale. If you want to see on the physical scale, then what you do is, so this is your ALU. This is the output from ALU. This is the input from ALU. So what you do is you design a feedback path, or you can also call it a forwarding path like this. Of course, you have to design a decision point here. So for example, if we look at these two instructions, you have the problem with R1, right? So value of R1 is ready over here. So you want to take the output of this ALU and bring it in here. And this is your control logic. So it would decide whether you want to read the value of R1 from the register file, or you want to get thing which is a feedback from ALU. Now, as I told you, we are not going to study the control paths because you actually become a designer. I wanted you to experience it a little bit, but unfortunately, since we won't be taking hardware description language now, and since you have not studied, which you should have in DLD, and of course, I understand the reason that the tool is available only on campus, and you can't expect people to have it off campus. So if you were doing that, then you would have to worry about designing a special logic so that it would decide whether to accept the feedback or you read from the register file. But anyway, so this feedback path will take care of problem like this. Okay, so that now instead of waiting for 2 cycles, when it finally writes into register path, you just get the output of ALU and put it into input of ALU. So that means your problem is solved. Does this make sense to everyone? Is there any question? Okay. So I will move forward.
Sir?
Yes.
Sir, will the feedback path will always be there in the ALU, or will it be there only when there is data dependency?
Okay. So the feedback path is a hardware thing. So and it will always be there. All you have to do is design this control circuitry in such a nice way that your hardware knows whether to accept this value or read it from the register file. So that is would be the job of a designer to make sure that correct value is taken. But the feedback path is a physical thing, so it will always be there.
Yes, sir. It answered my question. Thank you, sir.
Okay. Any other question? Okay. Now, two things. Let us consider two more things. You have taken care of one problem. Now let us look at another problem. Let us say your first instruction is add R1, R2, R3. The second instruction is add R6, R7, R8. The third instruction is subtract R4, R1, R8. right? So now you can see that there is no problem between first and second instruction. There is no data dependence. That means here first instruction is creating R1, but second instruction is not using R1 as one of its source operands. So there is no raw hazard. There is no raw dependency and raw hazard between instruction number 1 and 2. But there is a dependency between instruction number 1 and instruction number 3. Between 1 and 3. So now, you may ask that, let me try to draw this. So this is fetch, this is decode. Again, I'm drawing this on the time scale. So this is your time scale. When I say memory, it is always data memory. It is not instruction memory. This is write back. This is instruction number 1. Instruction number 2 at the same time would be, the time scale would be here. Right, and the third instruction would be like this. As you say, one instruction entering every cycle. Okay. Now, the value of R1 would be written in write back stage. Okay, that is number 1. And number 2, we have designed a forwarding path so that, output of execute can go on time scale like this. And on physical scale, it would be output of execute to input. So this is time scale, right? So, you have done forwarding path, so output from execute will immediately come to the input of execute at the same time. But here, this forwarding path is useless, right? Because if there is that forwarding path from execute of execute stage, this forwarding path is same as this forwarding path, it moves with the time scale. That, you don't want output from execute to go to the input of data because, this one does not require R6 because at this particular stage, R6 would be prepared, right? This one would have already been calculated and it would have already been starting to come out from memory stage. When the second one, the value of R6 is just coming out of execute stage. So you don't want that. You want something to come from memory stage to this stage. Why? Because at that time, R1 would have moved on from execute to memory and it would just be coming out of memory. Now, as I told you, memory stage, nothing happens to R1, it just floats through. So if I want to actually now draw a complete diagram of physical thing, so I'm drawing again this familiar 5 stages. So this fetch, decode, execute, memory, and write back. Then, and let us also show the forwarding, the data path like this. It is moving this way. Then you will have first forwarding path like this, and the second forwarding path would be like this. And of course, you will have a decision point here, whether you want to take output from the, whether you take the value of a source operand from the output of execute stage, whether you want to take a value of the source operand from the output of the memory stage, or you want to read from the register file. So at that time, you have to think of three things. Or when I say you, means you have to design a control circuitry which can decide, should I take output of execute as one of the operands? Should I take output of memory stage as one of the operand? Or should I go and read from the register file? So this one is also required. And your ARM7TDMI or any other processors which you have forwarding paths like this. So there are two forwarding paths which are absolutely required. And that is, one is from the output of execute stage to the input of execute stage, and the second one from the output of memory stage to the input of execute stage. Does this make sense to everyone? If you have any question, please let me know, because it's a very important conceptual point.
Sir, could you explain why the second forwarding path is needed again?
No, you mean why the forwarding path is required from output of memory stage to the input of execute stage?
Yes, sir.
Okay. So as I told you, that this forwarding path from output of execute stage to the input of execute stage is perfect for if you have a problem between instruction number 1 and instruction number 2, right? So for the kind of problem which we saw earlier between instruction I and J, that this one was immediately required here. So then you found out that if you have something coming out from output of execute stage and going back into input of execute stage, then it would solve your problem. So you can solve the problem between two instructions which are immediately following each other and they have data dependency. But now I'm asking another thing, that suppose there is no data dependency between first and second instruction, but what if there's a data dependency between first and third instruction? Will it cause any problem? So the first answer was yes, it will cause a problem, because when it would require to read the value at the end of data stage, at that time the value would still not be written into the write back stage, that means into the register. So it would still one cycle away. One option, once again, like is, you throw in one no operation or one bubble and your problem would be solved. But that is a bad operation, because you don't want to slow down your processor. In fact, you should think of some ways to increase the performance of your processor. So then the second option is that, okay, where is the value of R1 when the third instruction requires it? So it would have, at that time, it would just be coming out of memory stage, value of R1. It would, anything which is coming out of execute at that stage would be from the second instruction, that is R6. But the third instruction does not want R6. It wants R1 as one of its source operands. So an only way to get the value of R1 is take it out from memory stage and put it back into the input of execute stage. So that's why you require this feedback path. And as I told you, this feedback path, one needs to design the control circuitry very carefully, so that, say this, suppose this is coming from, this is suppose coming from register file. So one input is from register file, one input is from output of memory, and one is from the output of execute stage, all going back as one of the operands into execute. So then, you have one, the designer has to design this circuitry very carefully so that the correct thing is coming in. Does that answer your question?
Yes, sir.
Okay. So now, let us move forward. What about if you have a problem between first and fourth instruction? So let us
Sir.
Yes.
Sir, if all three inputs to execution stage have different values of some particular register, then
Right.
priority will be given to the middle one, means which is coming after execution stage, right?
Right. So, I mean, just 1 second. At that time, you have to decide, or your circuitry has to decide, which value should be taken. Now, that is a whole different thinking and logic will be used, that, what is the correct value. And then, you have to keep track of that register, because, it is not very difficult task. There are only 16 registers. So where is the latest value that one has to figure out? Is the latest value just out of execute stage? Is the latest value just out of memory stage, or it is in the register file? So whichever is the latest value of a particular register, that has to be selected.
Okay, sir. Thank you.
Okay. So now let us add one more instruction. And one more instruction is, say, another add. Now, once again, your problem, your data dependency, raw data dependency between first and fourth instruction, right? This one wants to use the value of R1 and this one wants to use the value, produce the value of R1. So the fourth instruction would be fetch, decode, execute, memory, and write back. Of course, you do understand that this is time scale, right? So this is time t equal to 0, t equal to 1, so on and so forth. So now, if you look at here, the value of R1 would be required at the output of here. At the same time, the write back stage is going to get finished. So then, you may ask, should I have a third path which is coming out from, say, write back stage and going all the way to the input of execute stage? Right? Do you understand the problem? It's the same analogy that, just when it is written, at the same time it is required in this input stage. So what should you do? Well, for that, they do a very clever trick, and probably you may have wondered that, why this blue part is shaded here on this side, whereas on the decode stage, it is shaded on the right hand side, and here it is shaded on the left hand side. So what they are saying is this, that, to avoid having this one more forwarding path, it is not necessary. What you can do is, you can design your register file in such a way that in the first half of the cycle, so that means if your cycle is like this, so this is one cycle. So in the first half of the cycle, you write into register file, and in the second half of the register cycle, you read from the register file, right? So first, you allow, in the problem like this, you allow R1 to be written in the first half of the cycle, and in the second half of the cycle, you read from that file and allow it to read from the register file. So isn't that a clever solution, that you don't require another forwarding path, but you do this? So the reason for doing this thing in a blue is that writing into register file is done on the first half of the cycle, and reading from it is done in the second half of the cycle. So that means you allow the write back stage to write into the first half of the cycle, and register read, which is part of the decode stage, is to be done in the second half of the cycle. So they can access register files, both stages can access register file, and they will not have conflict, because one is using only the first half of the cycle and the decode stage is using only the second half of the cycle. Is this problem clear to you? This is another important point, that you have done very clever use of register file and allowing the access to register file by different stages. Then comes, suppose then someone says, I've got the fifth instruction, which is again say add R10, R1, R7. Now that would be starting from here and ending over here. Now the fifth instruction has no hazard problem with R1 because by the time it wants to read, I mean, it will be this stage. Decode stage for that fifth instruction will be here. So it will be fetch stage. So this stage, by the time it wants to read the value of R1, it has already been written into register file. So you don't require any of the forwarding paths. So you don't require to read from the output of this execute or output of memory. It is already written into register. So there is no problem between instruction number 1 and instruction number 5. So the take home points are here. You have got data dependency between instruction number 1 and instruction number 2. You've got data dependency between instruction number 1 and 3. You've got data dependency between instruction number 1 and 4. And similarly, data dependencies between 1 and 5. If you don't provide a forwarding path, you have got a data hazard between first and second instruction. If you don't provide a forwarding path, you have data hazard between first and third instruction. If you don't provide read in the first half, write in the first half, read in the second half kind of solution, then you would have a problem between first and fourth instruction or hazard in first and fourth instruction. But even if you don't have any forwarding paths or any read in the first half, write in the first half, read in the second half kind of solution, you will have no problem between instruction number 1 and instruction number 5, even though there exists a data dependency. So the point to understand here is that data dependency is a program issue, whereas data hazard is going to be an implementation issue. And why do I say that? Suppose if I take the same problem and now I design a new processor which has got only 2 stages, right? So this one is fetch and decode. So it has got both. And the second stage is execute, memory, and write back, right? And this is not just a imagination. This is Cortex M0, which is a very successful processor in the market, has only 2 stages. And it is divided more or less like this. So now, again, you have 2 instructions, add R1, R2, R3. And the second instruction, which is immediately following it, is add R4, R1, R3. Now, as you can see here, you can now immediately identify that there is a data dependency between first instruction and second instruction, right? But will it create a problem in 2-stage pipeline? Then, you will say that you don't have data dependency in 2-stage pipeline, data hazard in 2-stage pipeline, even without any forwarding path. Because by the time when this comes out of decode stage and wants to read into write back stage, the write back stage would have already written in the first half of the cycle, and decode stage would read it in the second half of the cycle. So there is no problem of any forwarding path or anything. Okay, so we have clearly demonstrated here that once again, data dependency is a program property. That means the way you write a program, there would be dependencies between first and second instruction, first and 100th instruction, or first and 5th instruction. But whether those dependencies will be converted into hazard or not, if you don't provide any forwarding path, that would depend on the structure of the pipeline. That means how many pipeline stages are there. So one homework problem I would give you is, suppose if I have 7-stage pipeline, and this is also quite common. So this is fetch 1, fetch 2, And this is quite common. Usually in all modern processors, the fetch 1 and fetch 2 stages are there. Because fetch stage has to do a lot of work. And you'll realize why fetch stage has to do a lot of work, where you think is all you have to do is go to the instruction memory and fetch an instruction. But that in itself is a big task, because every time you may not get a hit, as we will study in the memory structure when we start studying that topic. So two fetch stages. Then there is one decode stage. Then there is one execute stage. There is this M1 stage and M2 stage. So you're divided up your data memory access stage into two parts. You're calling it M1 and M2, but the answer of a load and store kind of instruction would only be available here. Does anyone have any question? Rhythm? If you don't have any question, turn off your mic. And you have right back. So this is a 7-stage pipeline. And in next class, you have to tell me how many, or you have to think for yourself how many forwarding paths you would require. Once again, I will tell you the problem: fetch 1 and fetch 2. So the instruction fetch would end at this part. So at this particular point, your instruction will be fetched. It will be decoded over here, and you will require source operand when it is coming out from here. This is your execute stage as before. Your memory access stage again is broken into two parts, M1 and M2. If you have an instruction which actually accesses memory like load and store, then the answer would be available only at the end of M2. And this is your write back stage as you have seen before. Now you may ask why you are breaking a memory access into two parts. As I told you, if you want to make the execution even faster, then you divide up the stage which is taking slightly more time into two parts. So here you have broken data memory access into two parts, M1 and M2, and instruction memory access into two parts, calling it F1 and F2. Okay, so this is the homework problem. Does anyone have any question in understanding of this problem? Okay, so if you do this problem, then you will have a clear understanding that for a dependency to convert into a hazard, it depends on how many pipeline stages you have. If you have, say, just 2 pipeline stages, then you're not going to have any dependency getting converted into a hazard. If you have 5-stage pipeline, like what we studied before, then you would require 2 forwarding paths and one clever design like what we did, that write in the first half and read in the second half into register files. That kind of trick you have to do. If you have a 7-stage pipeline, then you will tell me how many forwarding paths you would require. And if there's a 9-stage, 20-stage, then you will tell me how many forwarding paths you would require. So is this problem very clear to you? So till now we have studied 2 very important points. We understood the definition of data dependency. We understood when data dependencies will be converted into a hazard. And number 3, what should we do to avoid a data hazard from actually taking place? Okay, so some of the solutions we saw was the easiest and the dumbest solution was that stop the pipeline for a couple of pipeline stages for at least this one, and then you push it forward. But that is no good answer. So the best answer was design a forwarding path. So now you may probably understand that for you, when you wrote a program, you never worried about data dependency or that getting converted into a hazard, because that problem was solved for you by the designers of ARM7 processor. So they already provided a forwarding path so that you get the correct answer. Clear?
Sir?
Yes.
Sir, I have doubt in where executing the whole means write back in half cycle, right?
Yes.
So, sir, whole time taking by cycle will be twice.
No, as I told you, the cycle, each stage here will take one cycle. So cycle is from rising edge to rising edge, right? So this is one cycle. What we are saying is that writing will be done in the first half of the cycle. So it will use only half cycle. So this is the write and this is read, right? So still the work for both of them is done in just one cycle, but each one, so this write back stage will use only the first half of the cycle, and register read would use only the second half of the cycle. Does that answer your question?
Yes, sir. But this in this manner, write back and read are taking half time with respect to execution stage and memory stage, right?
Yes. See, as
So
I told you,
all stages are not taking same time to execute.
no. I'll tell you. See, you have given one full cycle to register write and one full cycle to this decode cycle, right? Because those are the two stages which are using the half cycle and half cycle each into writing into register file. Now, you are providing one full cycle to register write, but it is using only half the cycle, and rest half the cycle it is doing nothing, right? So it is not such a bad thing, because it is a design perspective. So this stage is active only for half cycle, and other half cycle it is doing nothing. So that is fair. Same thing like data memory, other than for load and store, I mean the whole cycle is wasted for both algebraic instruction, data instruction as well as logical instruction. So I mean add or subtract or multiply or AND kind of thing would be doing nothing here. So it would be actually wasting the full cycle. But time taken through each one is one cycle. So whether it is doing work or not is a different thing. But one cycle would be spent for that stage.
Okay, sir.
Yeah, so it is a design choice, and it is design choice. If you look into it, it has got a purpose. See, I can ask you one question. I told you that most of the instructions, in fact, all instructions other than load and store does nothing into data memory. So why can't we give a pathway that all other instructions other than load and store can jump from here and directly get written into register file, because anyway it is wasting time, and we will be here quickening up the result. So isn't that a good idea? Or if it is a good idea, why no one is implementing it that way, or why it is not shown it that way here? Can someone answer that question?
Sir, because previous instruction is already in write back stage. So write back stage cannot take two instruction at a time.
Okay, but let us say the previous instruction is not in a write back type of thing. Sorry. It is a compare or test kind of thing. Still, you don't allow this instruction to jump from here to here. Okay, the answer for there is that there might be an instruction here which is of the load type, and in the load type of instruction you put in some value into a given register, say register R1, Now that value of register R1 would actually be written over here first. And then even if this instruction is again going to overwrite, say, register R1, then it is fine. So it is the principle of computer science that value of any variable, or in our case of any register, should be updated in the program order. You cannot jump. You can't say that, load is going to create one value of R1 and after that there is an add instruction which is going to immediately change it. So what's the problem? You can't think of it that way because, there might be other programs which might be looking at it. So this one principle of computer science is never violated. And that principle is always write the value in the program order, even if it is going to be overwritten immediately in the next cycle. Right? So you can't say that, value of R1 is going to change in the next cycle anyway, and who's going to use it? Don't think of it that way. So that is considered as a golden principle. You are not supposed to violate it. Is this clear? Can we move forward?
Yes, sir.
Okay. Now there is one problem. We have solved most of the problem except one set of problem. If you can give me just one moment. Okay. We feel that, we have solved all the problems by providing this forwarding path. But actually you would start asking yourself that have we? And the answer is here. Suppose you have this kind of pairing. A load followed by an immediate dependent instruction. So load is creating a value of register R1 or putting in a new value of R1. And the second following instruction is using it. See, previously, when it was algebraic instruction, where it was like add, sub or something, the value was ready over here. But for load, the value of R1 is not produced at the end of ALU cycle. It is produced at the end of data memory cycle. In ALU, only the address calculation will take place. So suppose if this R2 was replaced by some complicated thing that, R2 left shifted by 2 thing plus 10 or something, that would be taken care of. Address calculation will take place in the ALU, but the actual fetching of the value of R1 would take place only in the data memory stage. So the value of R1 would be available only at the end of this stage. Now here, there is no way you can go back in time. Right? This is a time axis, so you can't do that. So there is no type of forwarding would allow you to run your program smoothly. So in that particular case, you will have to have a bubble. So that means if this is the case, then you can't do anything but to waste the performance or degrade the performance by one cycle by putting in a bubble. And this is the only one, at least in the 5-stage pipeline. If I ask you this question in the 7-stage pipeline, then you will have to think again that how many bubbles you need to put in. So this is the only combination. You must remember this, that load followed by a dependent algebraic or logical instruction. That you cannot do anything. No forwarding path is going to help you. And you have to do nothing but wait for one cycle. Right? The only time it can supply you is this way. So that means if there is a following instruction which is dependent on R1, then it can be supplied. But other than that, you will have to wait for one cycle. Is this clear to you? I mean, this is the only difference.
Hello.
Yes.
Sir, I didn't understood why can't we put a forwarding path from data memory to value? In this
Okay.
case,
See, previously, designing paths was very simple when on the time scale, you are on the same instant, right? So on time scale, you are coming from here to here straight. So that means in physical sense, you are putting in a shorting it with a wire. That as soon as the output is here, it should go in here. So that is allowed and that is possible. But you can't travel back in time. It is like in going back to future. So I mean, if you want to come from here to here on time scale, that is not possible. So for that, you cannot have any forwarding path like this, because this is on time scale. You are trying to come back in time. You can't do that.
okay, understood. Thank you.
Okay. So is it understood and clear to all?
Sir, this problem happens with move instruction also.
This problem, will it occur with move instruction? You will have to work and figure out how move is taking place, because move usually is shifting, and move instruction will not access memory, right? Which two instruction accesses memory? Only load and store. They are the only one accessing data memory. For move, things are usually done in the execute cycle. I mean, you have to add a base to it or shift it or something, whatever it is done in execute stage. But memory stage is used exclusively for accessing data memory. And that can be done only by two instructions, that is load and store.
So means, sir, this problem can be solved if we use memory instruction in the starting, and in between the program we can use that move also.
Okay. So, I mean, I will tell you, I think you have put your thing in the right perspective. So just give me a moment to address that problem. So we said that, we have this problem. So load followed by an instruction like this. So then, this is the one, how to find out number of forwarding paths required. So this is what I already told you. So between the first and second and third and this one will have a problem, but this two will not have a problem, because if you keep on drawing like this, when you require the data on the fifth stage, at that time the write back is already done of R1. So you don't require any forwarding path, or don't even require this trick. For between first and fourth, all you do is you require this trick that writing is done in the first half by the write back, and then reading is done in the second half. Between first and third, you require a forwarding path from the output of memory to the input of ALU. Between first and second, you require a forwarding path from output of ALU to the input of ALU. Okay. So these are the type of forwarding paths you will require. Of course, you have to draw kind of a circle and with two crosses, which is like a control thing. So whether if you want to read a register, a particular value of a register, say R1, should you read it from the register file? That is the first option. Should you read it from the output of execute stage, or should you read it from the output of memory stage? And at every stage, your control circuitry has to decide which one to read. Okay. Now, as the same thing, if you say that, if you have three-stage pipeline, that fetch, decode, and then execute memory and write back, this was what is ARM7 is all about. Then you decide the number of forwarding paths that you may require in a three-stage pipeline. I mean, you will have to figure out yourself. And I also gave you another problem of 7-stage processor. So then, you also have to work on this one. So find out the answer for this too. I already showed you what happens for 5-stage and what happens for 2-stage. And I'm giving you a homework, what to do for 3-stage and 5 and 7-stage. The second kind of hazard is the exactly opposite of the first type of hazard. That is write after read. So now if you have an instruction I, which is like this. So you are using the value of register R1, and the following instruction is writing into the value of register R1. So this is exactly the opposite problem of the raw hazard. So here you may say, will it cause a problem? And the answer, as it is already written below, is that this kind of pairing will not cause a problem in an inline processor. Inline processor means whatever we have drawn, 5 pipeline stages in a row, that is known as inline. So in inline pipeline stages, it will not cause a problem. Why it will not cause a problem? Because if I is in front of J, then of course the value of register R1 would be read in the decode stage. And the writing by the following instruction will be done only in the write back stage, which is going to come after 3 cycles. So there is absolutely no problem, even without any forwarding path. This is not going to cause any problem to you. So war hazard, we will see that it is going to be a big issue when we study about superscalar processor. But most of the smaller processor, which are of the microcontroller type, which are inline processor, so just 5 stages or 3 stages or 2 stages, one after the other, it will not cause any problem. So that is known as war hazard, and it is also known as anti-dependence. Previous one, raw, was known as true dependence. This is known as anti-dependence. And the last one is known as wow hazard. So that means write after write. Or it is also known as output dependence. So that means you have got instruction I, which creates the value of R1, and then following instruction is also creating the value of R1. So as the computer science says, that R1 should be first written by instruction I, and then only instruction J should be allowed to make changes to R1. And once again, in inline processor, whether J is immediately following I, or it is like 2 instructions behind I, or 5 instructions behind I, it does not matter. So wow instruction, once again, it is going to cause a hazard if you have got superscalar processor, and we will see why it will cause a problem in a superscalar processor. But in your inline processor, this is not going to cause any problem. Okay? And it is also known as output dependence. So once again, to recap, in data hazards, in data dependency, there are 3 kinds of dependencies. One is true dependency, that is raw dependency. There is war dependency, and there is wow dependency. And each of these dependencies can convert into a hazard if the conditions are right, or depending on what hardware you are using. Okay. Now, one last question. Someone suggested that I said that this instruction and this instructions are always going to cause problem, and no amount of forwarding is going to solve this problem. So then compiler said that we are smart people. Can't we put an instruction from the program? Say your program is a 10 lines long program, and first line and second line is creating problem. It's like first line is a load and the second line is a subtract, and there is a dependency in register R1, and then I've got 8 instructions underneath it. Can I take out one instruction from below and put it in between load and subtract instruction, which are having dependencies, and push them at least one instruction away, so that this instruction will be pushed this way by one cycle so that I don't have to go back in time. I can straight away, my memory, the output of a memory will directly can go into execute. And that way R1 will be given. And I don't have to wait for anything. This will cause a problem. And this will also invite war hazard and wow hazard. Once again, a processor considers a program which is written by a programmer to be a golden program. So if you have made a problem in a logic, then it is your problem, right? In C program, if you have written a program in a bad way or you have written wrong logic, and if you're not getting the correct answer, it is not processor's fault. It is your fault. So processor considers that whatever programmer has given to me, I have to be faithful to that logic, even if that logic is wrong. So if a processor executes the programs in the order that a user has written, then it will never, or it should never cause a problem of war hazard or wow hazard for an inline processor. Why? Because as we declared earlier, that this type of instruction, this one would be read much before the following instructions want to write into R1. This is read in the second stage, and this is written into fifth stage. So even if they are following each other, reading will be done way before the writing is to be done, even if there is no forwarding path. But the problem will start arising, if my compiler tries to be very clever and say, okay, let me take one instruction from the bottom of the program and put it in between these two. And then, the problem of this, waiting for one cycle would be gone, and I don't have to, waste my performance. Then your compiler has to be very smart. As they say, you are allowed to break laws, but you should not be caught. So same thing is here. So I've given a problem here, and I want you to find out, this is a question directly from one of the exams. And I want you to find out all possible dependencies between all possible instructions without making changes. So it works like this. This is the first instruction. The 0th instruction is, for common parlance, is the first one. So you have to find out dependency between this and this, 0 and second, 0 and third, 0 and fourth. Then you have to look for dependencies between 1 and 2, 1 and 3, 1 and 4. Then you have to look at dependencies between 2 and 3 and 2 and 4. And finally, between 3 and 4. Okay. So you have looked for dependencies, and that would allow. So if you ask me that, this is a problem over here, can I take one of these instructions? Can I put it over here? So can I take this third instruction and put it over here? Well, obviously you can't do it, because what you will be breaking? Which hazard will you be inviting if you put third before first? What hazard will it create?
Wow.
Yes. So if you put third before first, then the value of R1 would first be created using this, and then this value will come. So that means you have going to cause a problem for this instruction, because this instruction was expecting this value of R1 and not this value of R1. But if you take this and put it in front of this, it is going to cause a wow hazard. Then you should start asking yourself, can I put second instruction in between 0th and the first instruction? So I'm giving this to you as homework. And why am I giving you as a homework? The reason is very clear. This will teach you compiler tricks and what can be done and what cannot be done. Sometimes as a designer, you are kind of stuck that, I cannot do anything. I cannot come back in time. So then only compiler tricks can work. And compiler trick is, can I switch between instructions? Can I push one instruction before the other so that, number one, my performance is improved. So that means I don't have to wait for any number of cycles. And number two, my program result should be correct. Now, as I told you, if I don't switch any of these things, then all I have to do is I have to put in one blob or one no operation between here, and that my hardware will automatically do it. My compiler doesn't have to do anything, and the rest of the program will work nicely. There will be no war hazard or no wow hazard. There is only raw hazard between here and here, between 0 and 1. But if I start playing with this, now can I put in the third instruction in front of 1, or can I take fourth instruction and put in front of 1? Then I'm playing with fire. Then I'm inviting war hazard and wow hazard to come. But one should not be afraid that will it invite war hazard or will it invite wow hazard? One has to be careful. One has to check. So this trick is very important to identify all the hazard. Is actually giving you a signal whether any instruction can be moved from here and put into this particular position. So I can ask a question like this. Suppose this register names are not given. They're all X and Y and whatever. So I mean, X and Y could be anything. And if I ask you a question, that can I take instruction number 4 and put it on top of instruction number 0? How many checks do I have to do so that there is no raw hazard, there is no war hazard, or there is no wow hazard? Understand this once again. It's a 5 instruction program starting from 0 to number 4. I am asking you a question. Can I lift this instruction number 4 and put it on top of instruction number 0 for whatever reason? And if I want to do that, and if I want to do it correctly, how many checks do I have to make sure that I have no raw hazard, no war hazard, and no wow hazard? So you have to tell me the number of checks. So just for example, if I want to put this one over here, then, and don't consider these values. Consider them as like just Rx, Y, Z, Rx, Y, Z or something. So if I want to put this over here, then first I have to check, will it create any hazard between 4 and 3? Will it create any hazard between 4 and 2? Will it create any raw hazard between 4 and 1? Will it create any hazard between 4 and 0? So all those checks for raw hazard will have to be made. So you will have to check your 2 operands, R1 and R2, and then see that any of the previous one, is it changing its value? Here, obviously it is changing the value here. This one is not changing the value. This one is changing the value. And this one is also changing the value. So if you don't know what these values are, then, you will have to make 1, 2. So 1, 2, for R1, you'll have to check with this. That is 1 check. R1 with this, 2 checks. R1 with this, 3 checks. And this R1 with R2, 4 check. Similarly, R2 with R1, first check. R2 with R4, second check. R2 with R1, third check. And R2 with R2, fourth check. The total 8 checks I have to make just to make sure that there is no raw hazard created if I take 4 and put it in front of 0. Similarly, you figure out how many checks will have to be made to avoid wow hazard and avoid war hazard. So don't go by these numbers. I mean, just put X, Y, and Z so that you know that these many checks have to be made even if you don't know what it is. So in fact, you can write a C program such a way that it takes any program as input, and if you ask it a question, that can I put instruction number 4 above instruction number 0, it will make all these checks and give you the answer that yes you can or no you can't. Is this clear to you? Okay, so 2 types of questions can be asked here. Number 1 is identify all the dependencies over here. So dependency is a program property. So, you have to find out dependency between 0 and 4 also. You can't say that, in a 5-stage pipeline, there will not be any problem between this R2 and this R2, because hazard may not be that, but dependency is definitely there. And then, the second part of question might be that, for a 5-stage pipeline, is there any hazard? So then, you have to identify dependencies, and then in the second column answer whether the dependency will be converted into a hazard or not. Okay, so we stop at this point. Does anyone have any question?
Sir,
Yes.
sir, by changing order, aren't we violating the law that program should be executed in order?
Okay. So as I told you, doing the program in order will never give you any problem. But living in Ahmedabad, you know that if you want to go faster, then you can overtake some vehicle even by wrong side. Now, of course, it is a hazardous thing, so you have to be very careful overtaking a vehicle from the wrong side. But this is exactly the same way that you are taking a risk, or your compiler is taking a risk, but it is taking a risk in a very informed way by checking if there is anything going to go wrong. And if something is going to go wrong, it will not do it. Does it answer your question?
Yes, sir. And sir, here we have only 5 instructions, so it is easy to check. But
Yes.
in actual program, there are much more instructions, so
Sure.
it will be more difficult to check all of them.
Yeah, so but nowadays programs are faster, and you can actually write a C program as a wrapper, and you can give as an input a 1,000-line program, and it can, or it should check dependency or give you all dependencies, and then you ask a question: can I move 3 in front of 0, or can I take 2 and put it in front of 0 or above 0? Those kind of things can be done, and in previous classes, such example was homework assignment was given that write a C program for which given any input, which is a small program written in a pseudo ARM assembly language, is that going to cause a problem? Okay, any other question? Okay, so we stop at this point, and we'll meet again